Okay, hi everyone, welcome back to this video series on data centers. Per-VLAN Spanning-Tree. So if you're running Common Spanning Tree CST, which means you're running only one instance of STP in your switched network with redundant links, there will be an election to choose what STP considers the best route bridge for your network. That switch will also become the route for all VLANs in your network, and all bridges in your network will create a single path to it. And as you know, you can manually override this selection and pick whichever one you want that makes sense for you regarding your particular network. Figure 12.5 shows how a typical route bridge would look on your switched network when running CST. Notice that switch A is the route bridge for all VLANs, even though it's really not the best path for some VLANs because all switches must make a single path to it. This is where Per-VLAN Spanning-Tree PVST Plus comes into play, because it allows for a separate instance of STP for each VLAN. It frees up the individual selection of the most optimal path. PVST is a Cisco proprietary extension to 801D STP that provides a separate 802.1 spanning tree instance for each VLAN configured on your switches. All Cisco proprietary extensions were created to improve convergence time, which is 50 seconds by default. Cisco iOS switches run 802.1D PVST Plus by default, but the NX OS runs RSTP PVST Plus by default. It's a newer, faster protocol that's also backward compatible if you happen to connect a switch running STP to a Nexus. No worries, I'll talk more about RSTP really soon. Creating a Per-VLAN STP instance for each VLAN is worth the increased CPU and memory requirements because it allows for per-VLAN route bridges. This feature allows the STP tree to be optimized for the traffic of each VLAN by allowing you to configure the route bridge in the center of each of them. Figure 12.6 shows how PVST would look in a switched network with multiple redundant links. This route bridge placement clearly enables faster convergence as well as optimal path determination. The convergence of this version is really similar to that of 802.1 CST, which has one instance of STP no matter how many VLANs you have configured on your network. But with PVST, convergence is on a per VLAN basis. Figure 12.6 also illustrates that we have a nice efficient route bridge selection for each VLAN. So here's figure 12.5 with a few switches, servers. Rapid Spanning Tree Protocol 802.1W. Wouldn't it be wonderful to have a solid STP configuration running on your switch network regardless of switch type and still have all features we just discussed built in and enabled on every one of your switches too? Rapid Spanning Tree Protocol, or RSTP, brings that amazing capacity right to us. Cisco created proprietary extensions to fix all the sync codes and liabilities the IEEE 802.1D standard threw at us, with the main drawback to them being that because they're Cisco proprietary they need additional configuration. But RSTP, the new 802.1W standard, brings us most of the patches in one concise solution. The only prerequisite is that you've got to make sure all the switches in your network are running the 802.1w protocol first. RSTP or IEEE 802.1w is essentially an evolution of STP that allows for much faster convergence, but even though it does address all the convergence issues, it still only permits a single instance of STP, so it doesn't help to take the edge off suboptimal traffic flow issues. And as I mentioned, to support the faster convergence, the CPU usage and memory demands are slightly higher than those of CST. The good news is that Cisco NX OS runs the Rapid PVST by default, a Cisco enhancement of RSTP that provides a separate 802.1w spanning tree instance for each VLAN configured within the network, but all that power needs fuel, and through this version addresses both convergence and traffic flow issues. It also demands the most CPU and memory of all solutions. RSTP wasn't meant to be something completely new and different. The protocol is more of an evolution than an innovation of the 802.1d standard, which offers faster convergence whenever a topology change occurs. Backward compatibility was a must when 802.1w was created, so RSTP helps with convergence issues that were the bane of traditional STP, and Rapid PVST Plus is based on the 802.1w standard in the same way that PVST is based on 802.1d. The operation of Rapid PVST is simply a separate instance of 802.1w for each VLAN, and here's how it all breaks down. RSTP speeds the recalculation of the spanning tree when the layer 2 network topology changes. It's an IEEE standard that redefines STP, port, roles, states, and BPDUs. RSTP is extremely proactive and very quick, so it doesn't need the 802.1 delay timers. RSTP 802.1w supersedes 802.1 while remaining backward compatible. Much of the 802.1d terminology and most parameters remain unchanged. 802.1w is capable of reverting to 802.1 to interoperate with traditional switches on a per port basis. And to clear up confusion, there are also 5 terminology adjustments between 802.1d's 5 port state and 802.1w's compared here respectively: disabled, discarding; blocking, discarding; listening, discarding; learning, forwarding. Make note of the fact that RSTP basically just goes from discarding to learning to forwarding, whereas 802.1d requires 5 states to transition. The task of determining the root bridge, root ports, and designated ports hasn't changed from 802.1d to RSTP, and understanding the cost of each link is still key to making these decisions as well. Table 12.1 shows the IEEE costs based on bandwidth that STP and RSTP use in comparison to determine the best path to the root bridge. Link speed cost, revised IEEE specification cost, previous IEEE specification: 10 gigs 2.1, 10 gig 4.1, 100 Mbps 1910, 10 Mbps 100. Let's take a look at an example how to determine ports using the revised IEEE cost specifications in figure 12.7. Can you figure out which route, bridge, and alternatively which are the route and designated ports here? Well, because switch C has the lowest MAC address, it becomes the route bridge, and since all ports on a route bridge are forwarding designated ports, well, that's easy part, right? But which would be the route port for switch A if paths between switch A and switch B were both gigabit? Their costs would only be 4, but since they are fast Ethernet links instead, the cost is a whopping 19. A quick glance at a link between switch B and switch B tells us that a gigabit link with a cost of 4. The cost of the link between switch D and switch C is 19 because that's also fast Ethernet link, bringing the full cost from switch A to switch C through switch B to D to a total of 19 plus 4 plus 19, which equals 42. The alternative route through switch A directly to switch C with a total cost of 19 is actually the lowest, making FA01 on switch A the route port. For switch B, the best path is through switch D with a cost of 4 plus 19 equals 23. This means that GI01 will be the route port for switch B between switch A and switch B. Because switch A has the lowest bridge ID, FA02 on switch A wins that role. Any port not mentioned here would go into blocking mode, non-designated, to prevent loops. If this seems confusing, remember that this process always unfolds in the following order. First, find your route bridge, then determine your route ports, and then your designated ports. The best way to get it down is always to practice. So let's take a look at another example shown in figure 12.8. Now tell me which bridge is your route bridge. Since all priorities are assumed default, SWC would be the route bridge because it has the lowest MAC address. You can quickly see that SWD has a direct gigabit port to SWC, switch C, so that would be the route port for SWD with a cost of 4. SWB's best path would also be direct gigabit port to SWC with a cost of 4. But what about SWA? The route port for SWA can't be the direct 100 Mbps port with a cost of 19, but the gigabit port SWD and then the gigabit port SWC can with a total cost of only 8. Not so hard. Multiple spanning tree protocol 802.1s. Multiple spanning tree protocol MSTP is also known as IEEE 802.1s, gives us the same fast convergence as RSTP but reduces the number of required STP instances, allowing us to map multiple VLANs with the same traffic flow requirements into the same spanning tree instance. It essentially allows us to create VLAN sets, so clearly you would opt to use MSTP over RSTP when you've got a configuration involving lots of VLANs, resulting in CPU and memory requirements that would be too high otherwise. But there's no free lunch, though MSTP reduces the demand of rapid PVST. You've got to configure it correctly because MSTP does nothing by itself. This brings us to figure 12.9, which shows how we configure MSTP to allow optimal path determination for each VLAN without the overhead of PVST. Figure 12.9 shows how SWA provides root bridge services for the sales, finance and marketing VLANs in a single VLAN instance, and how SWB does the same for the management, engineering and CD VLANs. This shows each switch capitalizing on the benefits of PVST without overhead drag on their CPUs. Convergence. Convergence occurs when all ports on bridges and switches have transitioned to either forwarding or blocking modes. No data will be forwarded until the convergence is complete, and yes, that means that while STP is converging within the given VLAN, all host data will cease to transmit until that process has concluded. If you want to remain gainfully employed, it's a good idea to make sure your switched network is designed to ensure that whichever version of STP is running on, it converges quickly toward that goal. Figure 1210 shows you some great network design samples for implementing STP on your switched network so that it'll converge efficiently. Convergence is vital because it ensures that all devices have a coherent database, and it will require your time and attention to make that happen painlessly. The original STP 802.1d takes 50 seconds to go from blocking to forwarding mode, and I don't recommend changing the default STP timers. You can adjust those timers for a large network, but the better solution is not to use 802.1d at all. By creating your physical switch design in a hierarchical manner as shown in figure 1210, you can make your core switch the STP route, which will shorten your network STP's convergence time nicely. Another good reason that typical 50-second convergence time can be a bad thing is because it's long enough to cause timeout problems affecting your servers or hosts, especially when you've got to reboot them as a result. To address this hitch, you can disable spanning tree services on individual ports with the Catalyst iOS using Cisco's Portfast Nexus, which runs RSTP by default. Takes convenience a step further by allowing us to configure the ports to be either edge ports or network ports. This capability speeds up convergence time even more. Figure 1211 illustrates how a switched network would look with the ports configured as I just described. If hosts are connected to a port, you would individually configure it as an edge port with no worries, because if it ever receives a BPDU, it can immediately change into a switch port. But if you're connecting switches together, you've got to configure these ports as switch ports, which will start out in the discarding role in order to make sure no loops exist. Once a BPDU is received, the switch determines if it can be the root bridge, if it already is the root bridge, or if it should remain in its discarding role to prevent loops. If a network or switch port doesn't receive any BPDUs, it will place itself in a designated role. Configuring spanning tree and Nexus. Spanning tree is actually configured pretty much the same way on Nexus as it is on an iOS switch, and it's verified with the same commands, but I'm still going to demonstrate how to configure the port types I just described on a Nexus switch. You set ports to edge only when connecting a host, printing server and so on to them, and only if that port doesn't connect to another switch. Remember, if a port in edge configuration receives a BPDU, it'll turn into a network port thinking it's connected to another switch. The port will then automatically become part of the STP process. So here's how you'd configure a port to operate in edge and network modes. Nexus 7K #INT E3 4044, Nexus 7K config if range spanning tree port type edge. Consider the interface as edge port. Enable port fast network. Consider the interface as inter-switch link normal. Consider the interface as normal spanning tree port. Nexus 7K config if range spanning tree port type edge warning. Edge port type port fast should only be enabled on ports connected to a single host, connecting hubs, concentrators, switches, bridges, etc. to this interface. When edge port type port fast is enabled, can cause temporary bridging loops. Use with caution. Edge port type port fast will be configured in 5 interfaces due to the range command, but will only have effect when the interfaces are in non-trunking mode. Nexus 7K config if range int e3 4548. Nexus 7K config if range spanning tree port type network. Notice that we configure our switch ports as edge, network or normal, which is the default and is always part of all STP instances. Setting the port to edge enables port fast on it, meaning that port is not part of any STP instance. It will immediately go into forwarding mode when a host is connected. Pay attention to that warning I received when I get some ports into edge mode. Plugging a switch into an edge port would cause temporary bridging loops in NXOS. In iOS switches, this would cause a major bridging loop unless you set up BPDU filters. But with NXOS, the port will automatically convert to network mode when it gets a BPDU. Let's take a look at configuring and verifying spanning tree on NXOS. Make a note to self that you can only configure either rapid, PVST or MST. Nexus 7K spanning tree mode MST, multiple spanning tree mode. Rapid PVST Per-VLAN Spanning-Tree mode. Nexus 7K spanning tree. BPDU filter doesn't send or receive BPDUs on this interface. BPDU guard don't accept BPDUs on this interface. Cost change in interfaces spanning tree port path cost guard. Change in interfaces spanning tree guard mode LCISSU. Configure line card ISSU type, link type. Specify a link type for spanning tree protocol. Use MST multiple spanning tree port. Spanning tree port options. Port priority change and interfaces spanning tree port priority. VLAN switch spanning trees. Nexus 7K config if hash sh spanning tree VLAN 0001 spanning tree enabled protocol RSTP root ID priority tree 2769 address 0012.43.62.8280 cost 57. Port 393 Ethernet 39 hello time 2 sec max age 20 sec forward delay 15 sec. Bridge ID priority 32769 priority 32768 sys ID ext1 address 0026.9823.7c41 hello time 2 sec max age 20 sec forward delay 15 sec. Interface role STS cost prior MBR type ETH31 DESG FWD19 128.385 P2P ETH3/9 root FWD 19 128.393 P2P peer STP. As you can readily see in the preceding output, there are lots of commands we can use to configure STP on NX OS. I'm not going into all of them here because again, that will be going outside of this book's purpose. Back to the output, when verifying STP, we can see that this bridge isn't the root bridge for VLAN 1. But look at the cost of the root, a whopping 57. That's a huge amount of links between our switch and the root bridge, which is off interface E39. If this were a production network, we definitely want to reconfigure our root bridge to be way more efficient for each of our VLANs. There's one last command I want to tell you about. If you want to skip all of this verification and configuration of the root bridge stuff, and no, you don't get to skip all of it if you want to pass the Cisco exams. You don't get to skip this either. So here's the command you can run on a switch to set it as a root bridge. Nexus 7K config Spanning-Tree VLAN 1 root primary. Configure this switch as primary root for this spanning tree. Secondary, configure the switch as secondary root. Nexus 7K config if Spanning-Tree VLAN 1 route primary. Did I mention that you've got to configure this on a per-VLAN basis, and that you can also set a primary and secondary switch as roots? Yep, you can, and it's certainly a whole lot easier than how we've done it in this chapter, but this is first and foremost a guide to prepare you for the CCNA DC exam, something you definitely want to pass. So make sure you know how to do it as we did, even though it really is the hard way. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.